Okay, so again, as this c gets closer and closer to 0, of course the integral is just the area under the curve between here and here. So that area keeps getting bigger and bigger. And there's no limit to how high this thing can go. Doesn't mean there's not a limit to how much area you can have. But there might well be no limit to how much area you can have, and this shows that that's certainly true. The fact that natural log of c approaches negative infinity tells you that your integral approaches infinity, okay? And all that means is that as c gets closer and closer to 0, there's no limit to how much area there is. No matter how much area you think you've got, you can let c be small enough that you have even more. Okay? So we define this integral as this. Okay? Okay, what about the integral from 0 to 1 of 1 over the square root of x dx? Well, if x is close to 0, 1 over the square root of x is a big number, right? Because you're dividing by a number that's approaching 0. Now, square root of x doesn't approach 0 as fast as x does. So that makes a difference, and it turns out that this integral converges, even though, as in the previous case, your graph looks a lot like this, okay? And there's no limit to how high this graph gets between 0 and 1. As you approach 0, it gets higher and higher without bound. Still, there's just a finite region, finite area, and it's simply because you don't have to do a limit here, okay? What's an antiderivative of the square root of x? It's 2 square root of x, isn't it? Okay? Well, that's easy to evaluate. You can evaluate the square root of 0. Okay? So you get 2. So even though this thing, even though the altitude, you don't need to let c go to 0 in this case because you can evaluate it, okay? Very straightforward. But that word that I had to squeeze in there's unbounded. Y values are unbounded, but the integral converges to 2, and we don't even have to do a limit. Okay? Now you can verify this. And actually, you don't even have to say 0 less than p, but I'll say it anyway because we don't really write it this way if p was negative. Okay? and for p greater than or equal to 1, it's unbounded. The reason is, if you take 1 over the square root, that's like 1 over x to the 1/2, right? Well, you get you don't end up with a denominator in your antiderivative, right? And as long as p is less than 1, well, your antiderivative is going to have a power of x that's 1 greater than negative p, which is going to be positive. And as long as you get a positive power in your antiderivative, you're going to be able to just evaluate it. As soon as p hits 1, well, then you have 1 over x, and we just showed that that one's unbounded. And if p gets bigger than that, well, you're still going to have some power of p in the denominator, right? Which is going to, again, behave the same way. So you don't necessarily have to know that. I'm not going to ask you to prove it. I would in an engineering calculus class, that and much more. But for an applied calculus class, I'm probably not going to ask you to do that. But that's something you could do. And it's worth thinking about because it helps you understand convergent and divergent integrals. Now, the other possibility for a divergent integral would be an integral that has an infinite region of integration. So we'll do that.